Okay, we're now recording. Thank you, Teddy, for letting me know. Again, we're discussing homework number 12. Homework number 12, here's a document that I copy and paste a bunch of questions from the electronic textbook. I did talk about how to do 6.35 part A. That was using the calculator. If I repeat what I just did, normal CDF, so I have to call up the second bars, option 2, and I made the lower -1 E99 and the upper 21 because the question is asking for the probability that a score is less than 21 with a mean of 25 and a standard deviation of 4. What's the probability that our score is less than 21 with these parameters? Well, if you define the lower as -1 E99 on the normal distribution going forever to the left, you got 21 somewhere over here. So you got the mean of 25 over here and a standard deviation of 4. And if you paste this to the home screen, enter, you get 0.159. So to actually show you the other answers, I'm not going to work through them because it just takes too long. But for part B, you get 0.013 with a mean of 50, standard deviation 9, and you want the probability X is bigger than or equal to 77. For C, D, and E, they're right there. So 0.6915, 0.9270, and that's just going to be 0. Mainly because 105 is so much bigger than 90 with a standard deviation of 2.86. So you're not going to really see any data points bigger than 105 if a mean of 90 and a standard deviation of 2.86, assuming a normal distribution, right? So that's that one. So using calculators there should be pretty straightforward. Let me go over the other ones where answers are provided. So for 6.41, here are the answers. And according to an NRF survey conducted by Big Research, average family spends $237 in electronics in back to school college spending per student. Suppose back to college family spending on electronics is normally distributed. So we're assuming normal distribution, of course, with standard deviation of $54, and you have the average or the mean, which is 237. You're asked to find, hey, what's the probability get less than 150? What's the probability spend more than $400? What's the probability spend between 120 and 185? Let's look at C. That's kind of a good one. If you want to do an in between, that should be really simple. You're going to do 120 and 185. So 120, 185. Remember this, the mean was 237. Standard deviation is 54. I don't know how I remember that. Hit enter, and there you go. So again, pretty simple, right? Actually, did I do that correctly? Yeah, so close enough. So that's 6.41. 6.45, let me show you those answers. Go back to the electronic textbook. So again, it's more of the same kind of jazz here. So the question here is, the Zumper National Rent Report lists the average monthly apartment rent in various locations in the United States. The average rent is $1,090 in Houston, Texas. So the standard deviation in Houston, Texas for renting one-bedroom apartment is $96. Again, we're assuming renting one-bedroom apartment. To normal distribution, what's the probability that apartment might cost that much money? What's the probability it might be between those two? What's the probability it might be that? What's the probability it might be less than $800? And this is kind of good to know because what if you have a certain budget, you're going to move to Houston, Texas for a job or go to college or something like that, and you need to rent an apartment and you have a certain budget, you're curious, like, you know, I'm looking for between $1,000 and $1,200. Cool. I'll probably be able to find something. If you have like a really low budget, like I can't spend more $800, and you realize, oh my God, like I can't find anything, maybe you don't move to Houston, Texas. So just something to keep in mind. So it has some relevance, right, to real life stuff. 6.47, let's look at that. Here are the answers there. So again, more of the same stuff again. So a lot of it is drill and kill to make sure you guys are comfortable with this. So again, the average income for someone who works in Boston is that much. The standard deviation is that much. They want to probably make more than 70K, under 55,000, more than $50,000, or between 57 and 65. Again, if you want to do more than what you would do, is go second bars. Like I'm right there actually. Why did I do that? Yikes. So $70,000. And you want to go forever to the right. So 70,000 and then everything to the right of it. So in this case, I'm going to do 1 second comma 99, because then I'm, just assuming you're making a gazillion dollars. And the average, which I don't remember from the problem, was 61162. So 61162. Standard deviation, I don't remember off the top of my head. It was 4246. 4246. So you get that. So pretty low percentage there. About 1.8% people would make that much money in Boston, according to this data. 6.49. I'll show you those answers in just a second. Again, a lot of it's just the same stuff over and over again. Just find the probabilities. So but you guys should be pretty comfortable with that by now. We've done this several times. Again, your mean's 88. That's your standard deviation. Just use a calculator, plug it in. You're good. Now, we still have some time to do the other problems. The ones where answers were not provided. So let me start with 6.38. So the U.S. Bureau of Labor Statistics reports that a person's usually work full-time. The average number of hours worked is 43.4 hours. I wish I could say that. I work way more than that. Assume that the number of hours worked per week for those who usually work full-time is normally distributed. So 12% of these workers who work more, 12% of these workers work more than 48 hours. Based on percentage, what is the standard deviation of the number of workers worked per week for these workers? Okay, that one's a little bit tricky. We will need the z-score there. So what we're going to do, so this is a good, I like this problem a lot. So z equals this, right? And this is x. No, I lied. This is x, 48. Minus 43.4 is the mean. I don't know the standard deviation because it asked for that. And I don't know the z. But we have another piece of evidence that helps. 12% work more than 48 hours. So if you assume a normal distribution, right, which we are. Remember, your mean's right here. And you want, and the mean, of course, equals 43.4. We know this also. Here's 48, and here's all this area. That has to be 0.12. So you're going to do an inverse norm, just so you know. So here's how it works. Second vars, option 3. We don't know the standard deviation though. Crap. So, let's do this. You're going to still be okay. Don't worry. Keep mu and sigma at 0 and 1. So we'll assume a different type of normal distribution where the mean is 0 and standard deviation is 1, right? So we know that 34% will be here, 34% will be here. So 68% is between -1 and 1. But if I want an area of 12%, what the calculator is going to do, actually, just so you know, it's going to give me the z-score that's 12% to the left. So what the calculator is doing when it does this, it's always going to assume whatever area is to the left. Well, it is symmetric, mind you, right? So you could kind of trick the calculator and say, give me the area that's 88% to the left, because that will be 12% right there. And that'll give me that z-score. Or if it's -1.17, you could just multiply it by -1 and use 1.17, which kind of makes sense because we know that when you're 1 standard deviation above the mean, 16% of data will be right here when that's 1 standard deviation above the mean. So a higher z-score would imply that lower percentage is being covered there. So we're going to go with 1.17. Or you could have just done this over again and did 0.88. So we were still okay. We just had to kind of trick the calculator So we get 1.17. There's a question in the chat. Yes, Will asked a great question. The inverse norm solves for the z-score, 100% correct. But you do have to make the mean 0 and the sigma 1, because that's the assumption for z-scores. It's standardized, meaning mean is 0, standard deviation of 1. Yes, that's 100% correct, Will. The 1.17, so let me go back to the problem again. So 1.17 is my z-score. Remember, you're going to be off to the right, so it's a positive z-score to right of the mean. So 48 minus 43.4, and now you solve for sigma. And if you do your algebra correctly, you should get 1.17 sigma equals 4.6. And if I solve for standard deviation, I'll need a calculator to do that. I'm actually glad I reviewed that problem because I could ask that on our test. So, and this is recorded, so you can watch this. 4.6 divided by 1.17, and you get 3.93. Now, you could check your work. If you go back to your calculator, second vars, option 2. Our lower is going to, well, we're going to do 48 and make that 1e99. So you're going forever to the right from 48. Our mean was 43.4. And our standard deviation was 3.94 as we solved for it. So I should get a percentage that's about 0.12. There you go. So I know I've done this right. So that's how you do that one. Going back to our work here again. So I'm glad I did that because I think that was when we had to talk about again. 6.42. Didn't want the mean egg production. So it's kind of a similar kind of situation as the previous problem. According to the U.S. Department of Agriculture, Alabama egg farmers produce millions of eggs every year. That's fantastic. Suppose egg production per year in Alabama is norm distributed. Great. With a standard deviation of 3 million eggs. Awesome. If during only 3% of the years, Alabama egg farmers produce more than that many eggs, that's a lot of eggs. That's 2.655 billion eggs. It's crazy. What does it mean egg production by Alabama farmers? Okay. So z-score. And we have our data point, that's x. We don't know the mean. We know standard deviation is 83. And we already do this in terms of millions. So I don't have to write 83 with a bunch of zeros or 2655 with a bunch of zeros. This is in terms of millions, so that's okay. And only 3%, and that's a high number, obviously, because produce more. So it means that you really want this tail end here. So I'm going to do an inverse norm again. I'm going to use 0.97 because I want 97% to the left shaded. Because you always assume shading to the left when you use inverse norm in the calculator. So second vars, option 3. And let's do 0.97. Keep the same mu and sigma. So that is a standard deviation 1.88. Sorry, a z-score 1.88. 1.88 standard deviation, that's what I meant to say. 1.88 equals 2655 minus mu over 83. So now what you're going to do is you're going to just do a little bit of algebra, right? 1.88 times 83, which is 156.04. 2655 minus mu. Solve for mu. They get 2499 roughly. So that's on average how many eggs they make per year. So that's how you would do that one. So it's very similar to 6.38 where you solve for standard deviation. Here's where you solve for the mean. Then we have 3 more problems down below before we go to our breakout session. The Federal Reserve System publishes data on family income based on a survey of consumer finances. When the head of the household has a college degree, the mean before tax is that much money. Suppose 6% of before tax finance when the head has a college degree are between that much, okay? And his income's emergency, what is the standard deviation, blah, blah, blah. Okay. That one's going to be a little tricky for that one, but I like it. It's a good problem. So we don't know the standard deviation, but we do know the mean, and we want to be between those two numbers. So what I probably would wind up doing is this. Give me one sec here. And we will need both of these z-scores to cover about 60% of the area. So what I probably could do, let's find the z-score for this one and a z-score for that one. So this one might be a good bonus extra credit question because this one's a little tricky. So if I focus on 75,600, again, your mean was at about 82 or 85,200, and you had 75,600. So we'll get that area. And then, of course, and you have 94,800. And we'll need that area. And we can't assume that it's, or could we assume it's right in between? Actually, I think we kind of got lucky. This is the middle 60% there. 85,200 is actually right smack in between those two numbers. In fact, it's actually the midpoint of it. If you actually were to do 94,800 minus that, and this minus this, I think you would get 9,600 in each case. So this is the middle 60%. We actually got a little lucky there. So that means that this is 20%. So actually, I could, that's gonna be 20%, and that's gonna be 80%. So I kind of lucked out there. So I can find these z-scores now. Yeah, this was a little tricky. I won't ask this on a test because I think that's a little too much, but maybe an extra credit question might be good. So inverse norm, 0.2. Let's get that standard deviation. There's negative 8.4. If I do this again for 0.8, you get the positive counterpart of it, but just to be sure, 0.8. Yeah, 0.8416. So your z-score is in between those two numbers. So then when you work that out, you could solve for, yeah, and you actually could just do it for one of them. You don't have to do it for both of them. It's not really necessary. Just do -0.4 for Z1 and just solve for sigma. That's all. But that's a little much, I think. That was a little crazy. The other ones here are probably cut from the same class, so I think I'll kind of just forego them for now. So I think now is a good time to go to the breakout sessions. So what are you guys going to do in the breakout sessions? Let me stop the recording.